Welcome to this lesson on decomposition reactions. In chemistry, decomposition reactions are one of the fundamental types of chemical reactions you'll encounter. Today, we're going to explore how compounds break apart into simpler substances. Following the general pattern of a B arrow, A plus B, let's dive into understanding these fascinating reactions and see how they occur in nature and in the laboratory. A decomposition reaction is a chemical reaction where one compound breaks down into two or more simpler substances. Think of it like taking apart a complex structure into its individual building blocks. In this type of reaction, we start with a single reactant, which is a compound made up of multiple elements bonded together. When this compound undergoes decomposition, the chemical bonds holding it together break apart, resulting in multiple products that are simpler than the original compound. The general formula for decomposition reactions follows a simple pattern. A B arrow, A plus B here, a B represents a single compound that serves as our reactant. The arrow indicates the direction of the reaction. On the right side, we have a plus B, which represent the multiple products formed when the original compound breaks apart. This formula shows us that decomposition is essentially the opposite of putting things together. One reactant always breaks into multiple products. Decomposition reactions can be classified into three main types based on the energy source required to break the chemical bonds. First, we have thermal decomposition, which uses heat energy to break down compounds. Second is electrolytic decomposition, where electric current provides the energy needed to split compounds apart. Third, we have photolytic decomposition, which uses light energy to cause the breakdown. Each type requires a specific form of energy input, because breaking chemical bonds always requires energy. Let's look at a classic example of thermal decomposition. When calcium carbonate is heated, it breaks down into calcium oxide and carbon dioxide. The chemical equation is 2C(CO3 arrow C(O) plus CO2. Calcium carbonate is commonly found in limestone and seashells. When you apply heat to it, the thermal energy breaks the bonds holding the compound together, producing calcium oxide, also known as quicklime, and carbon dioxide gas. This reaction is used industrially to produce lime for construction materials. Electrolytic decomposition uses electricity to break down compounds. A perfect example is the electrolysis of water. The equation is 2H2O arrow 2H2 plus O2. When electric current passes through water, it splits the water molecules into hydrogen gas and oxygen gas. 2 molecules of water produce 2 molecules of hydrogen gas and 1 molecule of oxygen gas. This process is important because it allows us to obtain pure hydrogen and oxygen, which have many industrial applications, including fuel cells and rocket propulsion. Photolytic decomposition occurs when light energy breaks down compounds. A classic example is the decomposition of silver chloride. The equation is 2AgCl arrow 2Ag plus Cl2. When silver chloride is exposed to light, particularly sunlight, it decomposes into metallic silver and chlorine gas. You can observe this reaction in old black and white photography, where silver compounds were used in film. The silver appears dark, which is why prolonged exposure to light causes the photographic paper to darken. Let's review the key points about decomposition reactions. First, one reactant always produces multiple products. This is the defining characteristic that sets decomposition apart from other reaction types. Second, these reactions require energy input to break chemical bonds. Whether it's heat, electricity, or light, energy must be supplied because breaking bonds is an endothermic process. Finally, decomposition reactions are the opposite of combination reactions, where multiple reactants combine to form a single product. Understanding decomposition reactions helps us comprehend how complex substances break down in nature and how we can harness these reactions for practical applications.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.